Morning, friends, neighbors. Uncle Lee here with you. A little discussion on a continuation on polar coordinates. And this time we're going to be talking about the polar coordinates being a function of the angle theta, whereas the r, that directed distance, is being a function of the angle. In order to understand this particular presentation, one must first and foremost review the polar coordinate part 1 lesson. But what we're going to do this lesson is we're simply going to look at r as a function of theta. And as soon as we look at r as a function of theta, then we can implore what we know about derivatives and second derivatives and rates of change of functions. And that's exactly what we're going to do. So the first example is a very simple example. I'm going to look at r is equal to sine of theta. I'm going to open up my graphing calculator here and take a look at that rascal and just see what it looks like. Open up. Okay. So I'm going to go make sure that I'm in polar mode. And I am. If you notice, I am in polar mode. I was reviewing some of this earlier today. So I'm going to go up here to, I have the sine of theta right there. I'm going to turn that graph on, turn this graph off. These are some other graphs I'm going to look at a little bit later. And I'm just going to look at that graph right now. It's going to be graphed in blue. And that's the graph. Oh, and I have it with the bouncy ball. I have the bouncy ball turned on. And it looked like it went around twice. That's interesting. And so let's see what my window is set on. And if you notice, my window is set from 0 to 2 pi. I can change my x. I didn't need all these x's. So let's change this, and that way we can at least see it go around again. I'm just going to limit my x's and my y's. I don't think I need that many. In fact, I know I don't. Just get a graph. Bam. Oh. And keep in mind, I'm doing theta all the way around the darn circle. I mean, I'm going 360 degrees, 2 pi. We like to do radians. So I'm going 2 pi. So what's happening with that? Well, a good way to get a picture of what's happening, and I always like to use, let's go to the table. If I go to my table feature, and if I start my table at 0, what I'd like to do is do increments of, it's unfortunate, we could do, I think, pi over 12 would get all of the normal increments on the unit circle, sixths, fourths, thirds, but it's going to be too much for us to look at. So I'm just going to do sixths right now and see what's going on. So I'm going to start at theta equals 0, and I'm going to go pi over 6, and just see if I can't get an idea of what's going on. Pi divided by 6. And look at the table. And this is very nice. So I'm going for, these are pi over 6s. Going 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, which is pi. And I'm at 0, I start at 0, and then I go out to 1/2, a little bit, 0.866, closer to 1. And then right at pi over 2, I'm at 1. Right there, you can see, right at pi over 2, I'm at 1. And then I start decreasing again, go to 1/2. And then when I'm at pi, I'm at 0. But then if you look what happens when I go beyond pi, the r's start going negative. That's why the whole graph lies on the upper portion in the first and second quadrant. Well, we know sine represents the y value, and all those y's are going to be positive, and they actually do. So there is some connection, certainly, with some basic trigonometry. But that's interesting, and that's what you have to, although it does only take one rotation, or pardon me, from 0 to pi to graph the entire graph, that's not really the entire picture. The entire picture from 0 to 2 pi is it has to go around twice. As soon as it goes past pi, then the r's are beginning to be negative. Okay? And this is 3/2 pi, 1/2, 2/2, 3/2. It's at -1, so at 3/2 pi, it's back here at -1, and then it goes on. So that's just a nice little graph of a polar function. Let's see where we are with our presentation. And I do have I copied those tables on here so that we can talk about them a little bit better. This is the same graph. And this is what we're going to do with respect to the calculus of these polar equations. We're going to look at dr d theta. We're certainly going to look at dr d theta, the rate that r changes with respect to theta. And if I notice, as I discussed before, as theta increases to pi, my r's go up to 1, and then they begin to decrease. Well, this is pi over 2. Well, what does that tell us? Because of the increasing-decreasing test, which is ever present in our study of calculus, that if theta is between 0 and pi over 2, what's happening to dr d theta? Dr d theta must be positive. Because I have my r's are increasing up into pi over 2, and then at pi over 2 they decrease. So that would tell me that dr d theta is less than 0, and dr d theta is less than 0 between pi over 2 and pi. And we can certainly easy enough find the derivative of r with respect to theta, come up with a sign chart, and those are things that we will do in our future discussion, or future problems with respect to it. In like manner, you can observe this chart in the pi, 7, 6 pi, 4/3, 3/2, 5/3, 11, 6, 2 pi. And you can see again what the r's are doing. Okay? Gone to the graph. The r's are decreasing at -1, then they begin to increase again. So let's look at a little bit different graph, r plus cosine theta, just to review more of r as a function of theta. And this is the graph of, and I believe that that is the graph of r equals 1 plus cosine theta from 0 to 2 pi. Let's see if it is. Let's go to my graphing calculator. I think I have that one in there also. And I do. I have the 1 plus, what was that one? Was that 1 plus? It was 1 plus cosine theta. Right there it is. I'm going to turn this graph off. I'm going to turn this graph on here. This graph is going to be graphed in red. I want to make sure that my window is set well. I'm going from 0 to 2 pi, and let's look at this graph. Let's go see if I can do the window. I have -2,2 by -2,2, and let's see if I can get the whole picture. I can. I think I'm going to increase my x's a little bit just so I can see over here. So I'm going to go from -2 to 3. I might go from -1 to 3 just to get a better picture. And I think that's the picture that I had on my presentation there. I'm going to go down here, -1 to 3, and that's going to give us a nice picture. And I do have that in about, but I don't think that's the one. Oh, let me see here. Something's. This guy here, that's the graph of 1 plus cosine theta. That is not the graph of 1 plus cosine theta. Clearly not. Clearly not. That's the graph of 1 plus cosine theta. I'll bet you $5 to a donut, excuse me. I'll bet you $5 to a donut that the graph that I'm talking about here is this graph. I'm going to turn this one off. Keep in mind that, there we go. And that's the one I wanted to talk about. So let's go back here and get this guy correct here. Keep in mind, you're allowed to make a mistake. And teachers are allowed to make a mistake. There's a typo there. A couple times I've gone through this. So this is the graph of 1 plus 2 cosine theta. 1 plus 2 cosine theta. Now that is interesting. That's an interesting graph, and how did that happen? Well, let's look at the table. And again, I'm going to make sure that I do. And I have my table set, I have my table starting at 0. And I'm going to go increments of 1/6 pi. So I'm going to make sure that this is 1/6 pi, clear that out there, second pi divided by 6, and go up to my table. And those are 1/6 pi. And so I have 1/6, and now if I just look at the table, tables are so important. I love to look at tables. I have 1, 6, 2, 6, 3, 6, 4, 6, 4, 5, 6, 6, negative. And look at where the r's become negative, or pardon me, r's become 0. R's become 0 right there at 4/6 pi. So let's look at that graph that I have on my presentation. So that's what's happening. At 0, I'm out here at 3, and then the r's are decreasing all the way to 4/6 pi. That's interesting, because at 4/6 pi, which is going to be about 1, 6, 2, 6, 3, 6, 4/6 pi, it's going to be more like 2/3, sorry. Let me get that rascal out of there for a moment. So it's got, I'm going to have 1/3, 2/3, 3/3, 4/3, pardon me, 1, 6, 2, 6, 3, 6, 4/6. 4/6 is going to be 2/3 up here. That guy right there, at that point, at that angle measure of 2/3 pi, 4/6, what's happening, the radius comes down to 0. And then from here to here, I'd love to have a different color in there, Lee. From there to there, these are the angles. From there to there, the radiuses are going to be over here negative. In fact, from here all the way to here, the radiuses are negative. So this is going to be what? 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 7, 6, 8, 6. At 8/6 pi also, at 8/6 pi also, then it comes back to 0, and then from 8/6 pi, then the radiuses start to increase again. So that's why we've got this stuff here, that's this loopy thing going on here. It's because so far, then the radiuses become negative. They're negative from this 4/6 all the way down to 5, 6, 6, 6, 7, 6, 8, 6. Then at 8/6 they come back to 0 and come back around. And then we could also look at, and I will let you do this on your own because I'm going to go on with the video. We could go on and see where the r's increase, and then we could also certainly talk about, I'll let you pause that and think about this for a moment. You could talk about where dr d theta is positive, where dr d theta is negative, where's the r increasing, where's the r decreasing, things of that nature. But what I would like to do right now, in light of time, is I want to talk about areas bounded by polar graphs. Very important topic, and keep in mind, whoa, slow your roll. The topics in polar coordinates that we have to discuss in Calculus BC are not that difficult. They may be a little bit different, maybe since we've not been exposed to them a whole lot. You may or may not have been exposed to polar coordinates in your pre-calculus class. Some do, some don't. But it's fairly, it's not a difficult topic. Look at the particular first video on polar graphs, and it's pretty easy. But one of the applications of, calculus applications of polar graphs, is to find areas bounded by polar graphs. Little discussion on that. And the first thing we need to do is we need to recall the area of a sector of a circle formula. And this is basic geometry 101, the area of a sector formula. And what does that tell us? I have a circle, and I have a sector. This is a central angle there. And if I want to find that area of that sector, well, what is that area of the sector? First and foremost, it is a portion of the area of the circle. Well, what portion is it? It's a portion of the area of the circle. It's a fraction of the area of the circle. Well, what fraction is it? Well, this is what fraction it is. It is that angle divided by 2 pi times pi r squared. That's how much. I go theta divided by 2 pi. That's the portion, that's the part of the entire circle it is. Pi over 2 pi, theta over 2 pi. 2 pi is all the way around. And if I simplify that, this gives me the formula for the area of a sector. 1/2 theta r squared, where r is the radius of that circle, and theta is the angle that creates that sector, if you will. Easy enough, interesting enough. Well, what about this polar? I've come up with an arbitrary polar coordinate, a polar graph there, with no equation. And say I want to find this area, this sector here. This is not a circle, so I certainly could not use the circle formula. This is a polar graph. Keep in mind, a circle is a form of the polar graph. But if I want to find that right here, what I'm going to do, I've got this ray here of that guy, or this R, if you will, this is R theta, this is a different R, and this is alpha. But what I want to do is I'm going to look at a little itty bitty increment of that sector, if you will, a little bit of increment of the area that I want. So small indeed that I'm going to think about it as being a portion of a circle. The area of a sector of a circle, which is 1/2 theta r squared. Little itty bitty, just a little bit. So small, in fact, that these r's are the same, because polar coordinate, your r's change. We saw that the r's are different. In a circle, the r's are all the same. But if you're talking about a polar graph, the r's are different. But I'm going to take such a small little thingamajiggy increment of this that the r's are going to, I'm going to assume for a brief little time, brief little increment of theta that the r's are the same. That's exactly what I'm going to do. So I'm going to go 1/2 theta r squared, where this guy right here is theta. Whoa, this guy right here is theta. And I'm just going to use that formula that I got from the circle. And what is r? R is my function of theta, so it's going to be 1/2 theta f of theta squared. 1/2 theta r squared. And that's going to give me a little bit, I mean, that looks big, but it's not. It's literally big. So a little bit, you can't see it, but you can't see it. And what am I going to do then? What I'm going to do is add up a whole bunch of those little things. I'm going to add up a whole bunch of those. And we know about doing that. We've done, well, there's an even smaller one. Hey, because a lot of people say, oh, it's too big, I don't know. But this is not that big. Very, very small. And now you can almost say, hey, the r's are the same, so hey, I can use this formula right here. But what am I going to do to add up a bunch of those things from here to here? How do I add up? Infinitely many things. It's not a new topic with respect to calculus. How do I add up a bunch? I use that integration. Use that definite integration. And that's exactly what I'm going to do. And now my theta, my change, my increment in theta, just like when I was adding up rectangles on my x, y, and I had my bases of my rectangles, they kept getting smaller, and I stopped calling them delta x and I started calling them dx because they were so small. And that's the same thing I'm doing here. This is my theta here. That's my small increment of theta. And how do I denote a small increment of theta? That's my angle. I'm going to denote that with d theta. That's the angle of that sector. This is my function. So I have 1/2 theta r squared. 1/2 theta r squared. But theta, itty bitty, teeny weeny, itty bitty, that's going to be my d theta. And how do I add up a boatload of those rascals? Right here. I'm going to go from theta all the way up to alpha. And I'm going to start adding them here, and I'm going to add up all of these. And this is the formula to find the area bounded by the graph of a polar curve, which is nothing more, nothing less than the area of a sector. The formula to find the area of a sector of a circle. So it's going to be theta from theta to alpha, 1/2 f of theta squared d theta. Let's do one example. Very easy example. Oh, that guy right there, 1 plus cosine theta. That's that rascal. That's why I had that graph. And what I'm going to do is look at this dude here. And now I'm going to look at this guy that I tried to look at before. Got a little mixed up. I'm going to turn this guy off. And here's my graph. And what I want to do is I only want to find this area in the first quadrant. I want to find the area of that rascal, certainly not a circle, of course not, but I want to find the area in that first quadrant, easy enough. I'm going to use the formula that we just developed, and I'm going to go from theta equals 0 to theta equals pi over 2. And my r will be the 1 plus cosine theta. And I have a copy of that on my, this is the portion of that graph of 1 plus cosine theta in the first quadrant. And now I have my formula. I'm going to go from 0 to pi over 2, 1/2 f of theta, which is 1 plus cosine theta squared d theta. Easy enough. Take my calculator. Well, I'm going to use the fact that integration is a linear operator. We're going to pull that daggone 1/2 out there. Make things easier. I could leave it in there, but pull the daggone thing out. This dude right here, I'm going to use my calculator to come up with that. That guy right there, do not round until the end. You can actually find that, put that, go back to your home screen, put that in there, and then divide it by 2. So that area in the first quadrant of 1 plus cosine theta is approximately 2.178. I'm going to let you develop the area bounded by 2 polar graphs, which is easy enough to develop. So a particular easy, let's say more of a straightforward topic in Calculus BC. Thank you, and have a great day. Uncle Lee be coming back with you. Coming back at you pretty soon.